Hello, friends. My name is Oleg Petrov. I represent CRT. And today I'm going to talk about diarization of a speech. And together we'll follow the path from clustering to target speaker speech detection. CRT is a company that has quite a lot of employees, but I would specifically focus on the R&D department that has about 300 people. We have an international research lab based at the Litmo University. We do all sorts of research in our company, starting from speech recognition to face biometrics processing. And we take part in all sorts of challenges and competitions. So today we are going to talk about the challenge that's completed in May this year. It's a Chime 6 challenge. And in track second of this competition, we scored #1. The Chime 6 challenge is actually a speech recognition competition where you need to identify speech of 4 participants that are having lunch or having dinner. These lunches are recorded at 6 4-microphone Kinect arrays installed in different rooms. According to the conditions, we have 20 2-hour sessions. And as I said, there were 2 projects as part of this contest. One of them was devoted to multi-channel speech recognition, and it repeated the conditions of Chime 5 that was run in 2019, whereas the second one was also adding the diarization problem. So we were not only recognizing the speech, but also we were to identify the speech of the target speakers. That's what diarization is all about. Talking about the outcomes of track 2, you can see that we won with a big margin, leaving behind quite well-known universities that have been doing diarization and recognition for dozens of years. And because this was a voice recognition competition, the main metric was water array, WR, and our result was 20% better than #2. I would like to thank separately my colleague Ivan Medenikov, who helped me a lot with the preparation of materials. You can use these links to find the description of the complete pipeline that we submitted as part of this challenge. These are 2 papers. And I'd also like to say that as part of my presentation, I will leave some details about the system. And I will also leave the part about voice recognition and the algorithm that Pontecorvo University proposed in 2016, the GSS algorithm that allows algorithmically focus on the target speaker. So one of the challenges, our challenges in the competition, was to get good diarization so as to invoke this algorithm. Talking about the diarization problem, speaker separation, it's a very hard problem in the conditions that you've seen. Small amount of data, small number of different speakers, and horrendous acoustic conditions in which we had to work. All the spontaneous speech, and importantly, a lot of intersecting speech. More than 20% of all time, there were 2 and more people speaking at the same time. The contest organizers provided us a pipeline that we started with. It included voice activity detection, X-factor extraction. They were scored with a PLDA algorithm, and then the agglomerative hierarchical clustering was splitting them to several different speakers. I will be referring to the GR metrics. They correlate with DR quite well, and they speak to how accurately our system matches the reference separation markup. So we started using 34-layer wide ResNet X-vector extractor, and we got the best results using cosine similarities and spectral clustering, SC. As you can see, we reduced the error by using these approaches from 63 to 47%, so DR on DXET, which is already a good result. But I'd like to note that all the approaches of diarization built on clusterization have a strong drawback. They can't work with overlapping speech, and even a perfect system built on this approach will not be able to issue DER of less than 20%. So we started to look at other approaches. We encountered the following problem. All the other approaches that we were considering required a certain acoustic trace for each person, for instance, the I vector. We decided not to solve this problem initially, but to test it on the ideal segmentation. What happens if we have good vectors? Will we be able to build a good diarization based on that? We started building different network architectures, and we started with this simple network that for both the sound and vector was learning to understand the state in which the speaker was. Silence, speech but not from the target speaker, and speech of the target speaker. This approach allows us to get 66.8 DER on DefSet, which is not a very good result. We started to sort it out, and it turned out that the system tended to say yes too much. So we had too many false positives. So we took a certain threshold to filter out all results that were deemed to be not very probable. This allowed us to bring the error rate considerably down to 46%. And we started thinking, okay, we said, so what if we build a system that would immediately, in a single path, could predict the probability for each of the speakers that they are speaking. We had already built a system like that in a serious way. We were sending different permutation of the speakers, different vectors using different mix-ups and augmentations. We were allowed to use the oscillate data set that includes more than 800 of voice data to teach the diarization system. Of course, no threshold is required of Voxlab that was, and we got 37.4 of DER. But we have to remember that we did it based on the reference markup. And what if we didn't have it? So we thought of the following story. So we start with a clusterization of X vectors, then get the baseline clusterization, get I vectors, get new markup based on these vectors, get the new diarization markup, recompute the vectors again, and try to do it in a cycle. So this approach with re-estimation of I vectors allowed us to get about the same result as with the reference markup. We also use some post-processing. It's quite simple, median filtering, filtering out vectors below the probability threshold. And we also combined speech segments separated by short pauses. We were deleting speech segments that were shorter than 200 milliseconds. So the entire system looks like this. But we remember that we only used one channel. We started to figure out if we could use two channels. Simple reverberation algorithms show that this approach is possible. Averaging of per channel probabilities also provides an improvement. So we built a system like this, that using the attention mechanism was weighting channels differently. So the resulting system produced this kind of performance. So you can see we dropped down from 63 to 33 on the DER set, and we put this algorithm on GitHub, and you can use this link to get to it. It does well, exactly what we did as part of the competition, but perhaps a little bit worse, because talking about diarization, it's 6 to 12% worse than what we achieved during the competition in terms of WER, the same, and this is because of the fact that we, for simplification sake, didn't include everything that we tried during the competition. It's much simpler and didn't include our internal X-vector extractor.
Speaking in terms of the main limitation of the method we came up with would be the fixed number of dictors, and the main challenge for the future is about how we're going to move away from this fixed number, and the number of speakers can be reduced with the use of this particular schematic. We are only testing this. So far, we haven't had a chance to speak about this in more detail, but this is the exact challenge that we are going to face the following year. And I think this is it. That's all I wanted to say, and thank you very much for listening.